All right, let's go ahead and kick this off. Welcome, everybody. Thank you all for coming to the 5th annual Night Campus Distinguished Lecture. For those that don't know, this series is really our flagship seminar event of the year. I mean, we have some really amazing seminar series, as I think many of you know, the Bioengineering Seminar Series, the Entrepreneurship Seminar Series, but really this is the one that we do just once a year. We bring in really distinguished scientist, engineer, researcher, who gives us their perspective on their research, their career journeys, and of course, their perspectives for the future. We've had a number of really outstanding speakers in this series so far. So Stephen Gillette, who's now CEO of Google's Verily, Dr. Brian Drucker, who is the director of the Knight Cancer Institute, was one of our speakers, Karen Woolley from Texas A&M, and then most recently, the director of the engineering directorate at NSF, Dr. Susan Margulies, was here last year. So all, extremely distinguished people, incredibly creative thinkers, and today's speaker is no different than that. And it really gives me great personal enjoyment today to introduce our speaker, Dr. Joe DeSimone. I've known him for many years. In fact, he was a distinguished lecturer for me when I was at Georgia Tech a number of years ago, as a lot of the stuff you'll see today was really just getting off the ground. And he has a significant research ties to a number of UO faculty here, including Jim Hutchison, Mike Pluth, Ramesh Jasti, who I guess was an undergraduate when he was at UNC many years ago, and Paul Dalton. And I really want to mention that one of the main reasons that Joe is here is not because I knew him, but actually our students demanded you be here, Joe. And, so and we try to listen to our students. So let me tell you a little bit more about Joe. He is a distinguished endowed professor of translational medicine and chemical engineering at Stanford University. He holds appointments in the departments of radiology and chemical engineering, with courtesy appointments in the Department of Chemistry and Stanford's Graduate School of Business. His lab focuses on developing innovative interdisciplinary solutions to complex problems centered around advanced polymer 3D fabrication methods. And he's also very translational and entrepreneurial, as you'll see. And in that respect, his research is focusing on exploiting 3D digital fabrication tools to engineer new vaccine platforms, enhance drug delivery approaches, and improve medical devices for a large number of applications. Complementing those areas, his third focus is entrepreneurship, digital transportation, transformation, and manufacturing. Joe, as I mentioned, is also an amazing entrepreneur, and in that respect, he was co-founder, board chair, and former CEO of the company Carbon, which I think he'll tell us a little bit about. And in 2016, he was recognized by President Barack Obama with the National Medal of Technology and Innovation, which is the highest U.S. honor of achievement and leadership in advancing technological progress. He's an incredible researcher. He has over 350 scientific articles, over 200 patents. He's mentored over 80 PhD students through their completion and into careers. And if you look at the list of those trainees, an obvious strong commitment to diversity and inclusion. Joe has many awards, and he's having to stand over there uncomfortably while I'm reading all this, so I'm not going to go through all of them. But I'll mention just a couple: the U.S. Presidential Green Chemistry Challenge Award, the Lemelson MIT Prize, and he's one of only 25 individuals in the world that are a member of 3 branches of the U.S. National Academies: Sciences, Engineering, and Medicine. So really, really incredible. If that's not enough, I learned at dinner last night from Paul Dalton that Joe also has a bridge named after him, and there's a picture of that. So that's
a modest bridge.
Still,
there's a parking lot with lots of potholes, which is more appropriate.
Okay, well, regardless, it's a rare distinction. There's many things that we can aspire to be like you, and
careful what you wish for.
Having a name bridge. So in this talk, Joe's going to tell us about 3D printing of his lab activities, describing particularly the continuous liquid interface production technology, or CLIP technology, which embodies a convergence of advances in software, hardware, and materials to bring digital revolution to polymer additive manufacturing. And so I know many of you have interest in hearing him talk, much more than you want to hear me talk. So with no further ado, would you please join me in welcoming the 2023 Distinguished Lecturer, Professor Joe DeSimone.
Thank you. It's certainly really nice to be here and meet everybody and see all the different programs. It was nice to see the focus on the students here and the postdocs and the training. You know, sometimes I think what we do in life is focus more on the research side of things, and you know, the programs that you have here are really distinguished. And some of the things that we're trying to do at Stanford, I think, are being done here. The impact programs feel like what we do, but on steroids. So congratulations on that, and it's nice to be here. So thank you for that kind introduction. You know, often we come here too and ask to talk about what we do, and I thought I might just start with maybe why we do what we do, and people over the years have different answers to those questions. I think for people that might be a little bit older than me, may have been inspired by the race to the moon and Sputnik and chose to be aerospace engineers or thinking about those kinds of things. Or maybe it was Rachel Carson's book, The Silent Spring, and the global environmental movement that got started, inspired so many people. You know, or maybe in a more modern way, in Jennifer Doudna and gene editing, and inspiring a whole new generation of people in that regard. You know, for me, it was all about a great teacher at Ursinus College outside Philadelphia. And at the undergraduate institution, we had a great course in polymer science, which is rare for a small liberal arts college to teach polymer chemistry. And I fell in love with the topic. And it inspired me to go to grad school. And in particular, at the time in the 1980s, there was also the role of microelectronics and Gordon Moore and Moore's Law and what was happening, and the role that polymer science was playing in patterning and its issue in microelectronics. So I thought I'd sort of walk through that and its impact in my career. You know, making integrated circuits starts with light, pattern light with different wavelengths, and we've all been marching down to different wavelengths. That's sort of the chisel to make things, and as this wavelength got smaller and smaller, you can make smaller and smaller features. And the light is passed through a silhouette or a mask pattern, and that pattern, that light hits the polymer film and induces a chemical reaction. And with that, you can start to make structures that, if you didn't look under an electron microscope, it might look like a 2D pattern, but it's actually three-dimensional, maybe 2.5. And this is what we and others, you know, have been working on, and you can use those technologies to build up more complicated structures that are powering our entire microelectronics industry. And this is the area that I fell in love with, and so I went down to Virginia Tech for grad school because my advisor Jim McGrath had a project in this area, and I would work with researchers at Bell Core, which was a spin out from Bell Labs, Murray Bowden team, and my first paper. I actually got published after I went to Carolina, was in the area of lithography and e-beam resist for this field. So I've been really interested in this whole field for a long time. And we've published a lot of papers in this space, and we did it with roll-to-roll processes for molding particles. I'm not going to talk about that today. We got into using liquid and supercritical CO2 as a processing aid to avoid some of the water and solvents in this area, and even spin coating from CO2. It was a lot of fun. But let me review this process a little bit with you and see how it relates to the topic I'm going to talk about. So this is a silicon wafer, and it starts with dissolving a polymer in an organic solvent typically, and pouring that polymer onto a wafer that's spinning at a high rate of speed, spin coating. And the solution spreads out, the solvent evaporates, leaves a thin film, and then you start passing light through a silhouette. And where that light hits, it induces a chemical change in that polymer. That chemical change often changes the solubility characteristics. So you can come in with a solvent, remove certain areas where the light hits or doesn't hit, and you have a pattern that develops. And then you can take that polymer and expose it to usually some sort of oxygen plasma or something to transfer that pattern from the polymer into the silicon. And then you'll treat the silicon with different barrier layers, and then you start filling it up with metal. Often you overfill with metal, so you have to polish it back. And that's how you make a single layer of metal pattern on a wafer. And you do this over and over and over again, and you build up a complicated device. So that's the microelectronics process in about 45 seconds. And you cut up the wafer, and you have all these individual chips. So this is driving most of the world's economies today, right? And it's interesting to think about that, and Moore's law in particular, because what's happened is it's basically gone from tens of microns down to tens of nanometers. And you've all heard about Moore's law driving it down. And now these people are using extreme ultraviolet, almost X-rays instead of light, and you're making structures on the single-digit nanometer range. It's remarkable. But it's using light to make things. So ask the question, what if we wanted to use light to make macroscopic things, like we're doing on a wafer? Now, the wafer is typically about 7 layers of metal, and it's very thin. And if you're going to make macroscopic things, it's going to be fundamentally different. So let's look at that at a high level. A silicon wafer in microelectronics typically has about 7 layers of metal. Many, many, many steps per layer, as I just walked you through, to make a single layer. And then you have to do multiples of those layers to build up that structure, often 30 steps per layer to make that. And it's not uncommon for that single wafer to be in a factory for about 4 months, going through each step. 4 months in manufacturing something that's very, very thin. Okay, let's contrast that to making macroscopic things, which are going to intrinsically have to be thousands and tens of thousands of layers because it's bigger, just physically bigger. You can't afford 30 steps per layer because you can't afford it to be in a factory for years. It's got to be in a factory, in manufacturing for minutes because it's a commodity, like a running shoe. And you therefore is only 1 step per layer. And this is, to me, it's interesting to think about these two in parallel because we're using pattern light to make macroscopic things instead of pattern light to make just a few layers of thin things, okay? And this is the area we embarked upon. And so we developed a process for doing 3D printing that was a fundamental change on how 3D printing was done. We're going to use light, and we're going to use light at 385 nanometers, and it's going to be pattern light. And it's going to come up from a projection system from underneath a reservoir holding organic resin that's photochemically curable. Light's going to pass through a window at the bottom of this reservoir, a very special window, a window that's not only optically transparent, but it's permeable to oxygen. And those of you that are familiar with free radical polymerizations know that oxygen is an inhibitor of free radical polymerizations. It inhibits the solidification process, if you will, that light is imaging into the polymer. And what's going to happen is that this build platform will lower into this reservoir, we'll get very close to the window, it'll be a gap, maybe 100 microns, and we'll start illuminating with light, and it'll trigger the pattern forming chemistry that takes place. So I got an image of a printer here. You'll see this platform lower in. We're going to make this object on the left, and we're going to do it in a sequential way of a series of images. It gets really close, and then you'll see the light come on underneath. And it's printing it from here, this side down, and it's basically going to be drawing it out. And if you watch the Terminator movie, it's not unlike T-1000 rising out of a puddle of liquid. Okay, that metaphor for you. But you see it rising up. It's adhesively bonded to the platform, but not adhesively bonded to the window. There's a gap between the growing part and the window caused by the oxygen that inhibits the free radical chemistry. I'll show that in more detail. So it's basically pulling this object up out of a shallow puddle. This is a sped up video, but it's in almost real time. It's 100 to 1,000 times faster than traditional 3D printing. And when you print that fast, it opens up manufacturing opportunities, okay? And it happens to be a pattern, an object that would be very difficult to mold. It's got a symmetry that would make molding complicated. Well, all right, let's walk through this. Well, to develop a pattern that can be changed instantaneously, we rely on a digital micromirror display system. These are a series of tens of millions of mirrors on a surface that basically deflect light. And it's powering the projector in the room. And we employ this technology into 3D printers. Texas Instruments, it's well-known technology. And this is how you get a pattern that can change over time. The window is a very special window. The window is optically transparent, but also allows oxygen to come through. And this is a class of fluoropolymers that we started working on a long time ago. It's an amorphous form of Teflon. And so it's optically transparent, but it's among the most oxygen permeable materials known. Cousins to these materials are used in something you're very familiar with. What kind of product would be optically transparent and permeable to oxygen that many people know about? Contact lenses, your eye, right? This is a close cousin to that. And it's a perfect material to use for the window system. But let me, now that's a little screwy. It looks great on my screen. It looks great in the back. All right, here we go. So I'm going to show you optical coherence tomography image of a part growing. This is looking into the cross section of a part of resin. We put some particles in it so you could, as a contrast agent, so you can watch the flow. And this is a part growing up here, and you see the flow of liquid, and you see this gap. This gap is caused by the oxygen. Light is coming through from the bottom. This is a UV curable liquid, and it doesn't cure where the light's the most intense as it exits the window. Normally, it would cure, but there's a gap here. And this is, I'm not going too much detail, but you'll understand this. So this is a concentration axis here, general concentration axis here, and this is going from the window up into the resin, okay, in a Z direction. So let's walk through this. Light's coming through the window, and light is at its most intense as it exits the window. Now, the light intensity will decrease as a function of distance up into the liquid just due to the molar absorptivity of the resin, okay? That light is decomposing a photoinitiator. So that photoinitiator will decompose into radicals. So the radical concentration will basically follow the light intensity up as a function of distance. Now, in polymerizations, once you form a radical pair in a organically polymerizable medium that has oxygen, that radical will do one of two things. If oxygen present, the rate constant for reacting with oxygen is much higher than a rate constant for initiating a polymerization. So if there's oxygen present, it will get consumed, the radical will be consumed by the oxygen. And so the oxygen is depleting as a function of distance up into the resin because the oxygen is being replenished by the window. As the oxygen gets depleted, it's a semi-permeable membrane that will allow oxygen to go back and replace it. So there's a gradient of oxygen concentration by the window where the light's illuminating. And once the oxygen concentration gets down to a certain level, then the polymerization will take place. And this will have the polymer forming, and this distance is the dead zone thickness. And this is where molecular weight's going through the roof. This is where viscosity goes through the roof. And it's actually it's a gradient. It's a polymerization gradient in the Z direction. It sounds complicated, but we've mastered it. And we've mastered it because the printers are all software controlled. And it's a beautiful combination of fluid mechanics, reaction engineering, the mechanics of the part that's forming. Every step of the process, I think of it as a software controlled chemical reaction to grow parts. Because what's happening is you have the fluid flowing in laterally, you have the part adhered to the platform, and the printer, we can control every aspect. So we can lift up the platform off to the next increment. We can wait for the fluid to stop flowing, and then we can illuminate. So it looked like a movie, but it's flashing quickly, okay? And every step of the process we control exquisitely. And so we developed a printer that was, and in the beginning, it was really hard to tame. So we wanted to have a printer that could evolve over time. So we used a subdiscipline of mechatronics, and meaning that every aspect of the printer is remotely controllable with software. In fact, I was sharing with some folks earlier, our founding VP of engineering at Carbon was a founding VP of engineering at Tesla, Craig Carlson. He got to Tesla before Elon got to Tesla. And he brought out the Roadster and the Model S. And he worked with Elon for about 7 years and had enough. And then I hired him, and we stole about 50 people from Tesla. So Elon and I don't get along. But I say that because the Tesla car is built with the same DNA as our printer is built with the same DNA as the Tesla car. It's a software play. And we built that up, and all these printers are on the internet, and we do over-the-air software upgrades every 6 to 8 weeks. So the printers were visibly getting better over time because the physics and the simulations of our printing got better and better. and we understood it better, and we can get the printers better. And this allowed us to have a lot of people using the printers while it wasn't done, but they saw it getting better time. And it was a network effect. The more learning we got, the better for everybody the printers got. And we started building factories, or our customers started building factories. And this is what a factory with the Adidas factory. I know we're in Nike country, but this is we worked extensively with Adidas, and this is what a factory looks like to make things like these midsoles. And I'll pass these around. This is basically a centrifuge, or a salad spinner, if you will. And you'll see a pair of running shoes on that platform. And when the parts are first printed, there's excess resin on the part. And instead of washing them with organic solvents, which is what you do in the lab, these would get spun. Excess resin would collect at the bottom and go back into the printer. Start passing these parts around. And this is how we scale these things up. And you'll see on the insole of that shoe, there's a little data matrix. Every part has a unique record in the cloud. I think of every part as alive. We have its birth certificate. We know its software. We know what software file, which resin, which location, all the details. Here's a stress strain curve for each midsole going up into the cloud. It's like its grades in school, right? And then we have its death certificate and recycling. So all that, so it opens up new business models when you have that kind of data. Okay, printing fast and just making something brittle, nobody cares about. You need advanced resins. And both these parts I'm passing around are what we call dual cure resins. So light is not a great way to make a great polymer. And so what we basically did is do orthogonal chemistry. So it's a mixture of chemistries. And so, Carolyn Bertozzi just got the Nobel Prize for doing orthogonal chemistry in a cell. This is orthogonal chemistry in a 3D printer. So basically what we have is a free radical. We have about 15 volume% of the resin is free radically curable. And it's blended with polymers or monomers that form polymers via step growth polymerizations. So epoxy chemistry, polyurethane chemistry, cyanate ester chemistry. Here's an example of epoxy chemistry where we have diapoxide and a diamine blended with a photoinitiator and a free radically curable system. You mix all these together from two different cartridges, and you print it at 385 nanometers, and this holds the part together. And then we basically wash it or spin it clean, and then we do a step growth polymerization chemistry. And that chemistry can happen in an orthogonal fashion. It's basically a solid state polymerization in the form of a shoe or the pipe that I'm passing around. And that's how you get great material properties, using light just to set the shape, and then use polymer science to set the properties. So this is what we launched in the business. We started heavily in dental. About 40% of Carbon's business is dental. So the industry that Invisalign created, the transparent braces, their patents expired a number of years ago, and now they only have 50% market share of that industry, and we basically power the rest. And we also introduced the world's first FDA-approved 3D printed dentures. I'll pass these around. Now, don't get wigged out. These are not my dentures. But we have about 500,000 people now wearing the first FDA-approved 3D printed denture. And I want to show you a video of this.
For the last 45 years of delivering dentures or longer, there was always an unknown. When patients are looking for a denture, their biggest complaint is that they don't fit.
You think of denture making as a craft, I need a craftsperson. And Carbon can do it.
Taking a lot and making it less is what a mill does. Taking nothing and making it something is what a printer does. We don't want to make molds, we don't want to make jigs, we want to make final products. And when you make final products from the milling process, it is far less economical than when you make final products from the printing process.
There's three basic things. There's fit, there's comfort, and there's function. 3D printing brings all of those together. The accuracies and fit, comparably speaking to what was done even 5 years ago, has become so much higher in impact for patients and for clinicians across the country.
For somebody that makes dentures day to day, it's transitional, it's transformative. A lab powered by carbon will allow me to make probably the best denture ever made.
This is probably the product I'm most proud of. It's there's over 36 million Americans that don't have any teeth. It's very hard to get a job in the upper mobility if you can't speak properly, eat properly, and it's not reimbursed by insurance. This is significantly cheaper. When they're handcrafted, you go from it's 8 chairside visits typically. When you do it with light and intraoral scanning, it's 2. And if you lose your denture, you're back in that chair 8 times. And I've talked to people whose parents have Alzheimer's, and it's, when you have to have somebody go into that chair 8 times, and it can be horrific. You lose them, you just order a 4-pack. These are digitally made. And it just transforms the industry, and it's a big deal. So big part of our business is in this space. And then we do heavily foam replacement using elastomer lattices. You think about this in technology development, this is a bowling alley, and the first bowling pin was a running shoe, and it was with Adidas. And then other products started to happen. We did bicycle saddles, Physique Real and Specialized, and this has now 40% or 20% less maximum force on the sit bones with engineered lattices like this. And then helmets. Almost every NFL player now has a liner in their helmet that's printed with our technology. So part of head protection is a perfectly fitting helmet. And so heads get scanned. Now both Riddell and Visus and others now use the technology, and a lot of the D1 athletes as well. So elastomer lattices. Probably the biggest market is rigid plastics. You see the pipe that's coming around. This has taken us the longest time to implement. It needed the right materials, the right cleaning solutions. But this is a $100 billion market opportunity. Injection molding is $300 billion. So these are enormous markets to make things with light instead of with molds. And the opportunity of having a warehouse in the cloud without having inventory and storing inventory in climate controlled buildings for years and all those sorts of things. It's really transformative. What's really driving the business now is the fact that you can design products on a Monday morning and test them Tuesday afternoon. The final product, because normally you design in the cloud and you go from bits to atoms, you go to a prototyping technology, which is not your manufacturing technology, it's often not even the same material. And you do all that because you have to cut a piece of steel, the mold, to scale it up. And once you cut a piece of steel, the tooling, it's not uncommon for that tooling to cost $1 million. If you're making an electrical connector for an advanced electrical system in a car that just makes 8 connectors, that tool could cost $1 million. And it may have taken you 6 to 12 months to get it made. And once you have it made, you don't want to change it. You just invested all that time and money. So watch this slide transition very carefully. It's my best slide. It's a disintermediation of the design manufacturing process. Our customers are designing products on the means of production. Forget about the speed of the printer. This speeds designs and products. This is what's driving the business today. And it's really powerful to see design teams really move this quick. A lot of environmental stewardship when you start scaling things up, including biodegradable resins and dry post-processing and local for local production. We're working heavily in this, bio-based feedstocks, lots of opportunities here. This is a whole lecture in itself, but I don't have time to go through this right now. We've made as many parts this year as we made last year. These are enormous markets. My son is now the CEO of the company, and I got my life back, and it's fun to watch the company and the team move things forward. So I led the company for 6 years, as was mentioned, coming out of the University of North Carolina. I got my life back. I'm now at Stanford. I'm on the board of National Geographic. I chair the board of my alma mater, where I learned about polymer science. So now I got a chance to start a new academic lab after shutting down a lab. And I thought about reflecting on what we did at Carbon. And what was the most inspiring thing to me at Carbon? First of all, it was a team of people at Carbon, but it was also the team of people that used our technology to make things. This is a screenshot of all our printers, where they're at, and it's a live data feed if you go in the lobby of Carbon. If you look more closely in the United States, you can see where the printers are, and the intensity of the light is the number of printers under that light bulb. And I fell in love with people that make things. And manufacturing science is really dramatic to me. And so when I immersed myself at Stanford, and I started looking around, my colleagues were doing a lot of microsystems. And a lot of the tools they were using were direct write tools, meaning they're not going to scale those up. And there was a lot of challenges with that. Most of these were prototypes and test beds to prove a point or to understand something. And just to say something very simple that I think is profound, you don't buy stuff you can't make. Simple. You don't buy anything that people can't provide to you and make them. And so I decided to think about this, and I walked you through, what microelectronics did in Moore's law, basically 1 micron down to single-digit nanometers. We at Carbon used a system that had 75 micron pixels, basically the thickness of a human hair, and went bigger. But there's a gap here with what a lot of my colleagues at Stanford were making products from 1 to 100 microns. And so we decided to focus our technology and interest here to mine the gap in that space. And so how do we make high resolution 3D printing? Well, at one level, you just make the pixels smaller and smaller. And that's pretty straightforward to do, because you can use focusing optics to take that pattern of light and make the pixel smaller. And that worked pretty well. We always print the Eiffel Tower, show our globalness. 75 microns, 30 microns. Can you see that little guy right there? A 1.5 micron pixel size. So the same physics and chemistry of the clip process we're now using with 1.5 micron pixels. And we're doing manufacturing science. We run a film through the printer. We print the parts. It doesn't take long to print small things. And so we'll do this in a way that allows us to scale it up. And you see this film going through the printer here. We'll do some printing, advance the film, and just have this run over and over again, allow you to scale up things. There was a phase in my career where we were molding particles. And we used something called a print technology. Some of you may know about it. And it was using imprint lithography. And I talked a big story then. We probably only had 12 shapes, because we needed a master template etched in silicon that was hard to get. And we would make shapes that look like this. Well, now with light, we can start making things that are unmoldable. And it's really easy to change the patterns. And we clearly are making things that become unmoldable now. And further unmoldable particles, all made with light. And we like to study these particles. So these are some individual particles caught in a node of a sound wave where we can inspect them. This is a little choppy here on Zoom. There's individual particles. And again, it's a little choppy, but you can see these little particles dancing around, and we study these particles and look at their interactions, and working with Sharon Glotzer and others and thinking about what people do with particles with controlled shape. And we've been scaling these up and making large quantities of shape-specific particles. So lots of things about it, lots of applications, maybe in flow cytometry, capturing cells or abrasives and that sort of thing. XY resolution is not the whole story, okay? The challenge is it's really easy to keep light into a pixel of a certain size. The challenge is light's really tenacious in the z-axis. It goes way further than you want. And the way we do that when we make thick layers is we put a dye in the resin to absorb how far the light will go. And it works well for everything we do at Carbon, when you're making layers that are 50 to 100 microns thick. But when you're making layers that might be single-digit micron, the light will blow past where you want. And you have resin on the other side. And so to get high resolution, you need X, Y, and Z. So hold that thought, because if you have a channel and you're making a layer here, the light will go past that and cure the resin that in the previous layers that you already printed. So hold that thought and put it aside. We developed a new process that we call injection clip. The first one clipped continuous liquid interface production. The resin came in laterally. One of the challenges, the gap is only about 50 microns. and it's a mass transfer limited process. The chemistry will go faster than the resin will be fed. It's not a reaction rate limited process, it's a mass transfer limited process. So we thought, couldn't we inject the resin through the part, through a microfluidic channel that was in the design of the part to begin with, and mechanically push resin into that gap and speed up the replenishment of the resin using mechanical flow. So now we have resin coming through the part. And this works like a champ. And you can have some of the resin being fed from the channel and some of the resin coming laterally. You get to choose how fast you're feeding the resin. The resin come in different directions. And what's interesting is when you have a platform holding a part, it's kind of like having a drop of water between two sheets of glass. It's hard to pull them apart, right? You can slide them, but it's hard to pull them apart. Well, we're pulling two parts away from with a liquid between them. It's kind of like that. And so if you had a force, and we put a load cell on the platform, you could pick the platform up, stop, and then watch the liquid flow in. And there's a stress relaxation with that. Pick it up again, liquid flows in, and you can illuminate at different points on this curve to make a pattern. And depending on the cross section, there's more force if it's got a higher cross section than the smaller cross section. That's for traditional clip. When you're injecting liquid, these forces go away because you're pushing liquid into the gap. In fact, it's kind of like walking up to a wall with a fire hose. You're actually getting pushed back the other direction. So we can eliminate those forces. The printing goes way order of magnitude faster than the traditional. I already told you we're going 100 to 1,000 times faster. This is another factor of 10. On top of that, using a liquid that's being injected through the platform, through the parts as we create them. So another factor of 10 on speed. I'm not going to wait for this to play through. And you can start injecting different liquids. So when we started getting into this, this is before the war broke out in Ukraine. So we added another design. And we print different liquids now. Well, this was just an example of different colors. And we can do multi-material printing by controlling this. We just had this paper published. And what's also interesting is normally when you print, you have to have a lot of supports on a part to hold it onto the platform. Well, when you're pushing resin through and you're innervating the part with these channels, those forces go away. And now we've designed all the software where the software decides where the channel should be to minimize the forces. And then when we don't need the channel anymore, we close it with light. So we basically start pushing the liquid into different regions. And so now we can start printing things without supports, which minimizes waste to do that, and it goes faster. But the most interesting thing that we didn't anticipate is, son of a gun, the channels are open. Why is that? Because if we just had normal clip, light would cure that. The resin's oxygenated. And we can have a turnover rate that keeps it clear. So we've now eliminated one of the key problems with 3D printing microfluidics. And so look at this. So if we have channels, if you have a vertical channel, you don't have to worry about overcure. Light's going straight up. And you can make a vertical channel with a standard clip process or injection clip. As soon as your channel starts to deflect at an angle, when you're trying to print this layer, the light can go past and cure where you didn't want it to be cured. And these channels are filled with liquid. So with clip, we start overcuring and we can't make what we want. But with injection clip, we can keep these channels open, even a horizontal channel. And so now we're basically pumping resin through the parts into these gaps. And we now know the turnover rate that we need to keep the channels clear. And we're pumping the same resin that we're printing, and we're just putting extra resin through the parts. This is opening up negative space fabrication. So we're making nothing, right? Sounds like a Seinfeld episode, right? But we've now opened up all sorts of free-form microfluidic systems. And most microfluidics, as you know, if you made microfluidics, are made using the tools of the microelectronics industry, layer by layer. All the channels have a rectilinear cross-section. Right now we have free-form, and nothing in biology is rectilinear. Right? We have spherical cross-sections or oval cross-sections. And it's opening up all sorts of these kinds of structures. And so we're moving into a whole new area of making negative space stuff using 3D printing. And I just want to walk you through some examples. So I'll hit some of these pretty quickly. Microneedles. So most of us in this room, I think, are vaccinated multiple times. I got COVID from Bill Gates. That's a separate story. I'll tell you that later. But the source of the target for the vaccine are the migratory immune cells. We have 100 to 1,000 times more migratory immune cells in the dermis of our skin than you do in our muscle. So most of the vaccine is missing where the target is. People are very interested in intradermal delivery, but it's painful to put liquid into the skin, and it takes a talented person to put the syringe in at an angle. So microneedles have been around for a long time. Our lab is sponsored by the Bill and Melinda Gates Foundation. Our contention is that the microneedles have not been a reliable and repeatable dosage form because the designs you really want haven't been accessible with the current manufacturing technologies. And so if you look at the history of the way microneedles were made, they were made using the tools of the microelectronics industry. We call those Gen 1 microneedles. So over 50 years old, etched silicon, they're all the same height. Gen 2, we're making molds of those master templates and molding replicas out of new materials. What we call Gen 3 are direct fabrication methods that are scalable, not direct write tools. And Gen 4 are those with plumbing, enabled by iClip. And so let me just show you some of the papers we published. These are some early versions of our microneedles. These were a simple design. The vaccine was was coated onto these microneedles using a free meniscus evaporative coating process, pushed into the skin to deliver the vaccine locally into the dermis. And we compare that to an intramuscular injection. We have a 50-fold increase in antibody response. And this is published in PNAS not too long ago. Now with our high resolution printer, these are what the needles look like. And now we can sequester drops of liquid and freeze dry them or lyophilize them. And now it's a dry product that when you push it into the skin can be reconstituted with the liquid in our skin. So dry products can be shelf stable for much longer than liquid products, and we can eliminate the cold chain. I think we heard more about freezers during COVID and if you ever tried to buy a freezer during COVID, you know how real that was. But now we're designing microneedles in new ways with all different surface area. And this is what we can do with our 3D printer. Unheard of designs for microneedles. Continuous glucose monitoring. We are really excited about moving into this space. So that's a thing now, and it's really good. But the opportunity for sampling interstitial fluid, it's in order to get molecular information, it's very difficult to do venous puncture. Right? No one takes blood from a child. It's hard to get blood out of elderly. Maybe Theranos had it right, if you know that company, except for the fraud. And they went after the wrong circulation system. They went after blood. We're focused on interstitial fluid and the sampling techniques. Now, the challenge is what microneedles give you the best sampling of interstitial fluid. If you have a microneedle with a little hole in the tip, microneedles tend to clog because of the skin. And it doesn't take much to clog a little microneedle. Well, guess who figured this out? A long time ago. Mosquitoes, bees, my undergraduate started to recognize, the hole is off to the side. It's a biomimetic strategy for microneedle design. This works like a champ. And we're setting records now in the lab of drawing interstitial fluid out by having the hole off to the side without clogging. It's just really interesting to see these kinds of where ideas come from and where evolution's taken things. So we're really interested in negative spaces. We're printing columns. Most columns are packed beads. Every column's a snowflake. Every column's different. We want to move into digital chromatography systems, digital blood separation columns using margination and fluid mechanics to separate bacteria from blood. We have sepsis or move into dialysis. So we have a big interest in moving in this direction. And then the last thing I'll leave you with is, I think another big horizon for us is we have pyrolysis and 3D printing have a really interesting intersection. So carbon fibers, most people are familiar with carbon fiber composites. That carbon fiber is made from a synthetic polymer, typically polyacrylonitrile. You spin a fiber out of polyacrylonitrile. A fiber has a high surface to volume ratio, and you heat it up under under a certain environment up to 1200 degrees, and you can remove all the elements and just have pure carbon. And it has to have a high surface to volume ratio to outgas, and it shrinks isotropically into a fiber. Nobody pyrolyzes three-dimensional objects because you can't outgas and they fracture. Well, when you stitch together lattices, this looks like fibers to me. And we are now pyrolyzing these three-dimensional structures and designing 3D printable resins that optimize the formation of carbon, silicon carbide, silicon nitride, new boron-based materials, and they shrink isotropically when they're designed properly and printed properly. And this opens up really amazing opportunities for things like new electrodes in batteries, lithium-ion batteries, flow batteries, zinc aqueous rechargeable batteries, huge opportunity. There's a lot of research at Stanford in battery technology. It's sort of like, when in Rome, we're playing now with the Romans, and we're trying to move more into batteries. Electrocatalysis, supports for electrocatalysis. 30% of the carbon dioxide emitted in the United States comes from the chemical industry, from heating fossil fuels, burning fossil fuels to drive endothermic reactions. Everybody wants to electrify the chemical industry like they've electrified the transportation industry. So this is designing new ways of heating electrically, and the most energy efficient ways of doing that is inductive heating. So these are new silicon carbide based systems and flow reactors integrated with heating systems. So we're really excited about this new intersection of pyrolysis with 3D printing, opening up an entire new fields in a whole bunch of areas, and that's good. You'll see a lot more coming from our group in that area. So let me just thank the students. I had a great group of grad students. When I was at Carolina, most of my students were chemists, and I had about 10 to 15% engineers from NC State. Now at Stanford, I'm mostly engineers and a few chemists. A great group of postdocs, a couple of great master students, and a great staff and team. And these are my students, and it's appropriate having Alcatraz in the background with this group, if you knew them. And a lot of great collaborators. Kirk Frank's a key part of our group, collaborating a lot with Eric and Bob. A lot of the particle work is done with Heinrich Jaeger, and then a lot of the life sciences work being done increasingly with Tom So and Sharon Battieri and Matt Becker on some biodegradable systems. And then a team at Carbon. This was the most amazing experience in my life with this group. Hired 400 people, and it's an amazing business. And like I said, my son is now running that. I want to show this. This is on our website. We spent a lot of attention about the quality of our lab and the character of our lab. And I want everybody to know what our values are, so that you know that we're a destination for excellence wherever it comes from. And you can read more about this on our website. And the last thing I'll just point to, especially based on all the things being done here at University of Oregon, we have a Center for STEM Mentorship, and we focus heavily on teams. And this is a faculty member and their entire group. It's not mentorship for faculty or for students, but it's the group. And that's really, it takes a vulnerable trust to do that. And we have a big center, and we're really proud of what we're doing. But I must say, we're teaching a lot of the same things that you do here, characteristics of great teams. We have a lot of people that come in and talk to us. Teamwork and team culture, venture capital, leadership, communication and storytelling, which I heard here, science communication, work preferences, personality types. I'm proud of what we're doing, but I think what you're doing is what we're doing on steroids. And the opportunities that you all have here, you should know it's really remarkable, and it's rare. And really bravo to everybody here. And I just wanted to sort of point to that. So. And at Nat Geo, we think a lot about these same sort of traits of our explorers. The raison d'etre of National Geographic, like at a university which has its students and faculty, and Nat Geo, it's our explorers. And these are the characteristics of our explorers. And I think these are the kind of characteristics that appeal to me, and these are all the kinds of characteristics that I think great team players have. And it's really the intersection of being humble, hungry, and smart. And I think those are the things that you guys are really embodying here. And these are the things that really drive a lot of things forward. So with that, let me end. I'm a big fan of using light to make things. I think light's a powerful chisel. to craft things and craft things that are unmakeable and do this in a more environmentally sound way. And with that, thank you for the invitation to be here, and I'd be happy to answer any questions.
Yeah, I'm gonna like
Yeah.
we sort of do this living room type of thing. I know there's gonna be tons.
It's like Oprah Winfrey.
Yeah, I guess I'm Oprah.
You're Oprah.
Yeah.
I'd like to be Oprah, but
Yeah, I'm proud
you're
of
Oprah.
Thank you. That was not just thought-provoking, truly inspiring. So
Thank you.
just amazing what you've done over your career. I'm sure we're gonna have lots of questions. There are microphones going around. I'll just start with one. You kind of touched on one example of this with the mosquito and the bee, but I'm interested in sort of the ideation process, you know, that maybe led to carbon or whatever other example you want to talk about. You know, there are an amazing number of innovations that went into that printer. I'm sure you didn't conceive of them all at once. So, you know, how does that happen?
Look, diversity is a fundamental tenet of innovation. Diversity of thought and experiences. And like a lot of folks, I recognize patterns. You know, I've had a lot of different people through my lab, and somebody that's grown up with not much money thinks about problem solving very differently than somebody who grew up with a lot of money, as one example. And neither one is right. They're different. And in the ideation process, you want to really open the funnel. You want to have lots of different ideas. And I think all of us bring our experiences to the table. We spend a lot of time on disciplinary diversity. We don't spend nearly as much time or attention to human diversity. And how you cultivate an environment, you know, talking about what your values are so that you can open up the funnel is, you know, starts with that kind of leadership, right? And to make sure that you create that environment. And then you get different learning styles. I got some people that are like in the moment for talking and engaging. And I got other people that 24, 48, 72 hours later have just as much content, but it's delivered later. So you got to have mechanisms for bringing in all those kinds of styles. So it's just paying attention to how do you engage people in the broadest way. When you teach organic chemistry, you know, not everybody can see spatially. And so it's like teaching the same thing 4 or 5 different ways if you really care enough to get people to engage and understand. And so I think it's those kinds of elements that are key. And that takes a vulnerable trust, because you're putting your ideas out there, and not every idea is a good one. And, you know, I worry too that some places think every idea is a good idea. And so you got to be able to have an environment where you can engage in that debate. Not every idea is a good idea. And to be able to push back, and I worry a little bit too now in 2023, coming out of COVID, coming out of, you know, post George Floyd, with social media and cancel culture, that I think a lot of people are afraid to speak up. I think there's a silence emerging to put, you know, even to simply push back on an idea. There's some people like, why bother? It's not worth pushing back. And I hate for that to happen, because you got to have, this takes friction in a comfortable, safe environment. You want to cultivate friction. And to have a great innovative process, you've got to have friction. But how to do it in a safe environment is really critical. And talking openly about that is a key to the innovation process. That's a long-winded answer.
No, that's a great answer. Very philosophical. All right, Danielle.
Hi, Joe. Thanks so much. That was really beautiful. So I'm going to start with, I guess, a more global question. Then I have some more specific technique materials questions, if I can keep the mic for that long. So you just talked about bad ideas. So I'd love to hear some of the bad ideas, that, because we heard about all the successes, and they are long and wide. And you know, I've been following your career for as long as I could read journal articles, and it's been incredible. But I think to normalize failure or bad ideas would be wonderful for me, and also for the crowd here.
You're trying to make me cry. I alluded to a semi-good idea that wasn't as good as I talked about with molding particles. We never got to the range of shapes from a simple molding process that I was promulgating. Not close. And then separately, the company only focused in a really narrow area and didn't blow out. It's one of the reasons I agreed to be CEO, because I've been disappointed by too many of the CEOs that I've hired in what the decision making that companies do. That's a separate topic. That's one example. I'll give you a really now I'm on the verge of maybe crying on this one. So we had the idea to use liquid CO2. And I'll give you the two examples. One is in dry cleaning to replace perchloroethylene, spun out micelle technologies. And we built a process, designed a process using liquid CO2 in dry cleaning. We had 70 dry cleaners around the United States. One of the dry cleaning machines I remember was in the front of a shopping center right next to an ice cream store, and people would get their ice cream and watch the CO2 dry cleaning machine. It was like amazingly interesting human dynamic. But it was more expensive than using perchloroethylene. And I believed the EPA was going to come through and help us move this forward. Legislation never moves as fast as you expect. Perchloroethylene is a human carcinogen. It's the most common way that people bring in human carcinogens in a household is bring in dry cleaning. You know, a lot of people are not wearing as much dry cleaning, but to introduce an environmentally sound but more expensive technology into an industry that's declining. The dry cleaning industry has a negative CAGR. Now, I didn't know I thought CAGR was a party. It's a compounded annual growth rate, and the dry cleaning industry was declining. And you don't introduce a new, more expensive technology into an industry that's got a negative CAGR. That was the most challenging time in my career as a young professor, starting a company, our first company. And the businesses were not being successful as a franchise model. Ken Langone was on our board, if you know who that name is, Langone Medical Center, and he is brutal. There's two Ken Langones in one body, at least two. He's a great philanthropist, but he's a hard business person. I can take anything now because of my time with Ken Langone. Nobody can rattle me because he did. And we were running out of money. We had the best financing discussion we were ready to do a deal. And I was in the World Trade Center on Monday, September 10th. And I remember I flew to Denver from New York. My kids thought I was still in New York. I landed in Denver. I remember that night because it was the first time the Denver Broncos played in their new stadium on Monday Night Football. And then the world changed the next day. So unwinding that business was a colossal failure. And lots of lessons learned through that. So, I bring to you, carbon's a great story. Micelle was not. And I do think there's a lot of lessons learned. And in business school conversations, though, we often start there. And thanks for grinding me down.
I encourage some of the students to ask questions.
Just as a faculty member pops up this evening.
You spoke about fluid injection models being used on the smaller scale. I was curious if you also found them useful for larger scale things like what carbon was doing, or if it was not as applicable there.
No, I think it's very applicable there. The printers are pretty fast now, and they could go faster. I think it's pretty. So this is a debate. So companies have to focus, and what you're seeing are next generation products. And I think there's a time scale when they'll be implemented, but it's also thinking deeply about what is the killer app. And I do believe that negative space as a category feature is a killer app for us, and it's probably going to start there. And as it bleeds more further into other products, I think time will tell. And then I think multi-material printing will be a next horizon with that. Not many people yet really want multi-material printing. I mean, people talk about it a lot, but if you think about the actual people that want to commercialize things, you know, it's hard to really squint at something that's of significance.
Joe, building on that question, how, if you go, you talked about mining the gap, how big can it go? Are we going to see Joe DeSimone bridges that are made with your technology?
I hope not. So I think there are other techniques. So when you start making bigger things, the cost goes down in some ways. So people are 3D printing houses. That's really a computer-controlled extrusion process. People are using 3D printing to do cakes, and it's computer control. You know, I don't find those nearly as compelling. When you can make something other ways, you know, lattices you can't make any other way. So I really think about, I start first and foremost with of high value, high demand products that can't be made other ways. So and we chose the printer sizes. The smaller, the M-class printer we did at Carbon basically can make like 40% of the plastic parts on an average car. And the bigger printer, the L printer, can make 60% of the plastic parts on an average car. We did that product market analysis, and both those printers can make almost everything in medical industry. So it's a general printer, and we looked at product market fit, and with some, you have to make some decisions. And I don't know that people are going to really need bigger printers. I think the area that you see driving metal-based 3D printing is being driven heavily by rocketry now. And it's really exciting what's happening. But those are really complicated things that can't be made any other way. Those printers should be able to, somebody needs an innovation in metal-based 3D printing that makes it faster. That hasn't happened yet. So they're laboring through the traditional sintering processes, but they're making really massive things that can't be made any other way. So I think those are the key intersections. Yeah.
All right. One last question.
And I'm stealing the last one. This was a fascinating talk. I had a question about kind of you as leading an academic lab. It seems like you have quite a bit of different expertise going on, you know, fluid dynamics and chemistry. And is that something that is integral to kind of making good science, or can you focus on more niche things?
Oh, there's room across the board. I mean, it is our thing to integrate a lot of different things. That's what we do pretty well. Our core, you know, we're polymer science in unusual ways or unusual media. That's sort of, you know, whether it's CO2 or molding or 3D printing, we're polymer people. And I love the collaborations. And somebody asked me earlier about, you know, learning. I never had any formal training in medicine or biochemistry even. And you know, we learn new stuff, you know, through my students. That's what I love about academia. And you know, when you're CEO is a hard job. It's really, most people, they romance, you know, starting and all that companies, and it's brutal. And I've got as many negative stories like the dry cleaning one at Carbon, played over and over again, that we figured out. And it's a brutal series of stories, but at the end of the day, you know, you won, and your team, you know, it's just that winning through adversity, during adversity is hard, and we enjoy that, and it's a really great experience. And so that's always been great. But I think at a university, and I don't want to say too much about, I think it's like being at a spa. Now, my faculty colleagues may not, everyone's like, what is he saying? But, you know, the idea of working at this ecosystem, you know, when your product is really the students and people, that's a privilege in life to be able to do that. And we can't forget that opportunity. And so to me, I think it's learning all these different disciplines and learning is a great life experience. And so I try to do that in our group, and it's mostly living vicariously through my students to do that. Their job is to teach me stuff.
good friend of mine who's president of the Chinese University of Hong Kong said we shouldn't be talking about publish or perish, but collaborate or crumble.
Oh, I love that. That's a good one.
So we have a reception, so we can continue the conversation, but let's thank Dr. DeSimone one more time.